Okay. Okay. Shall we start? I think we are going to introduce something very central in probability. It's about here we call it the mean. There are a few other names that go with it. First, we have to have a random variable in mind. So we are not taking the mean of an outcome of an experiment. Outcome of an experiment can be non-numerical, so it doesn't make sense to take the average. So all we are talking about is some random variable. And the random variable, because of the coding, you always code the outcomes into some numbers. So it makes sense to talk about averages of numbers. All right, so we can think of we have a few names for it, but they all mean the same. So one is called the mean of the random variable x, or the mean value of the random variable x, or the expected value of the random variable x, or expectations of x. So they all mean the same thing, all right? So I think sometimes we don't quite stick with a very strict name, because we do slip into using alternative names for the same thing. So basically, this is the situations here. Let me illustrate this with some simulation results. So basically, if you roll a die, you want to find out on the average, if you keep rolling the die many, many times, what would be the average number that you will get from the rolling a die. So one way to think about it, I save my simulation results in a list or in a vector called A, and I sample it from 1 to 6. So this corresponds to rolling the die. I'm basically choosing 1 to 6, so like corresponding to rolling a die. And I'm going to do it, say, 600 times, because later on I would divide by 600, so it might be easier. The way it is done is I'm just rolling a die is similar to putting 6 tickets in a hat. One ticket is labeled as 1, and then the other is 2, and so on. So the replace equal to true means that after I take the ticket, I will note the number and then put it back. So I will go back to the original situations every time I'm doing it. And then now we should specify the probability of the tickets, which maybe some tickets are bigger, some tickets are smaller, so you have a higher probability to pick the bigger ticket. Now, if you don't specify the probability, this software assumes they are equally likely to be chosen. So I just don't need to. Otherwise, you have to specify ticket 1, what is the probability, ticket 2. So you can actually, by doing so, you can model an unfair die that you are rolling, all right? But now I'm having a fair die. So I rolled it 600 times. And so this is the early part of this. I don't want to show you the 600 numbers, but I show you the first 6, all right? So the first row, I get 1. The second row, I get a 6. The third, I get a 5, and so on. Or I can take a look of the last 600, all right? The last 6. So this is what I will get. Now, if I just do it this way, it will be 600 numbers. But it's okay. But a neater way to do it is to tabulate the result. So this is called table. So what it says is that now I have 101. I'm expecting 100. So the first thing is we do have some deviation. 100 is exactly what we will expect, all right, 100 times, but it is up and down. All right, so it is 101, 98, 85, 116, and so on. Now, to find out the average that I get from this 600 rows, of course, one way that I can do it is, this is a vector. Okay, I'll just take the average. So the average is just mean, all right? And so I will get this. Now, later on, this 3.5 is something special. That is the average, the population average that we are expecting when we roll a die, 1 to 6. So here, this is now pretty good. I have 3.5, 35. Now, one of the reasons why we are going to define the mean in this way is doing these calculations. Now, from this table, the one that I just showed, so I'll just, this is 101, and this is 105, and so on. Now, so to take the average, one way is that I add up the original thing, 1 plus 6 plus 5 plus, and then plus the last few, 352, and then divided by 600. So this is one way to go about it. But a slightly better way of doing the average, because I have done the tabling now, so I can actually have 101, because there are 101 of 1, so I have this. And then, so this is the frequency here. 101 is the frequency, and then 101 over 600 is the relative frequency. And so this is how I will calculate my average. 6 times 105 over 600. Okay. And later on, we will argue that from a frequency approach, these things, if I were to do it many times, not only just 600 times, many times, okay, so you can change it to the number of times. If you do it many times, this will converge to your ideal probability. That is the 1 over 6 that you expect. And so this is going something that we are going to define. So in our actual definition of the mean of the die, will be 1 times 1 over 6, and then 6 times, and I will have this. So that gives us the motivations why we are defining the mean in such a manner, because we actually have in mind this kind of calculations. Okay, so it probably would not come too abstract. Okay, so here it says that you are playing a lottery game once every week. We can actually calculate the total probability. I mean, if you buy the total, what is the price? What is the probability that you will get the jackpot prize, the number one prize? So here it argues that you are not interested in the actual number of the lottery. You are actually interested in either you win or lose. So your experiment here is drawing a lottery ticket. So there are many possibilities. But among the possibilities, all you are focusing on is whether you win or you lose. So only one of the outcome here corresponds to you win the ticket, and then the rest will be you lose, all right? This is assuming you only buy one ticket, but suppose you buy 100, then 100 of the outcomes here will correspond to your winning probability, and then the rest, besides this 100, will be all leads to your losing for that particular game. So the long run average amount won or lost per play is as expected value, or the mean value of the random variable that describes possible outcomes for a single play. So this is where the definition is. So here I have the definition here, but let me come back to explain this in a form that is similar to rolling the die. So suppose you perform your experiment many times. So you have, these are the possible values. So let's say I only have, for the time being, I have 10 of them. And then you perform it n times. So, and then you count the frequency that you get x1, and then the frequency you get x2, and then the frequency you get x10. So the total here would be equal to x1 times f1, x2 times f2, and then x10 times f10. So as a result, your average would be x1 f1 over n, x2 f2 over n. Okay. I jump a little step because the average should be this total divided by n, but I only divide the n into each of the f here. And so now the frequency thing is that we expect if we do it many, many times, this will converge to the probability of the x1, all right? Or depending on your notation, we have this probability. So this is the frequency approach, if you still remember how we calculate the probability. So all of them would go to the corresponding fx x2, and then this will converge to fx x10. So that is why this is our definition. That would be x1, f of x1, x1. Okay. All right, so that is how it motivates the definition. Now this definition, as it is now, is quite accessible, but later on we'll see the rest of the definitions are actually coming from the same idea. All right? Okay, so in a way this is an average. Now these are just percentages. So in a way, this is a weighted average of the possible values of the xi. If it is a weighted average, another way, if you think of it as in a physical manner, this is the center of gravity. If you are putting fx1, that is the mass there at the position x1, and then the position x2, you put a mass f of x2, and so on. So when you are summing this up, you are basically calculating the center of gravity. But once you think of it as center of gravity, one obvious implication of this is the center of gravity will not fall outside the range of your value, meaning that if x1 is your smallest value, your center of gravity can't be on the left of the x1. And if x10 is your largest, then your center of gravity again won't fall on the right-hand side of this. So it will be somewhere in the center. All right. So if you calculate your mean and the number that you see is outside the range covered by the possible values, something is wrong in your calculations. Okay. So we can define the mean expectations for continuous random variable in a similar way. In here, the discrete thing, we use a summation sign. And now in continuous case, we replace the summation sign by the integral. So this is how it is defined. So I guess if you, keep this in mind of how we calculate the mean is the same here. So one way is I can call it average, and this would be equal to 101 times 1 plus 98 times 2 plus 85 times 3 plus 116 times 4 plus 95 times 5 plus 105 times 6. Okay, so this will give me the total. So I wanted the average. So let me call what. Okay, so this is coincides with the same here because this is just another way of calculating this 600 numbers in the list here. All right. Okay, so basically, as I mentioned a few times, the annoying part of as of this stage now is one have to make a decision whether the random variable that you're looking at is discrete or continuous. For simplicity, there are only these two kinds of random variable. And if you decide that it is a discrete random variable, everything you do will be algebraic. I mean, like summation or subtractions. And then when you think that it is a continuous case, you will be doing mostly integration and differentiations. Okay, so this is the thing that I'm trying to explain with the visualizer as well as the simulations. So roughly speaking, the mathematical expectation is an average, or more precisely, a weighted average, weighted according to the probability that you will find yourself for that particular value. Now, in the discrete case and in the event of equally likely, then this is just 1 over n here, and so you will basically take the average of all the n possible values of the random variable. So here we are going to compute some of this. The expected value exists provided that the sum or integral in the above definition exists. At this stage, I think you can assume it will always exist, but later on, I mean, in your life, you might encounter situations that the integral or the summation sign does not converge. It might converge. It might go to plus infinity or minus infinity or some other things. Then the expected value will not exist. Now, note that the expected value is not necessarily a possible value of the random variable x, but it has to be somewhere inside the range, all right? Okay, so this is a fair die. So this illustrates the comment earlier. Suppose a game consisting of rolling a balanced die, a fair die, and we pay $C to play the game, and we get $K if the number K occurs. So this is the game. Okay, forget about C for the time being. So the game is saying that whatever number you get, your payoff is according to the number. So if you get a 6, you get $6 in your payoff. If you get 1, you only get $1 payoff. Now the question here in this example is how much you have to pay per game in order to make the game to be fair. Suppose you only pay $1 per game, and then your reward will be according to the number you get. Then this game is favorable to you, right? Because you can only get even when you get 1. But when you get anything bigger than 1, you will definitely gain, right? So the game is, is to your advantage. So here they're trying to argue what would be a good choice of C so that it would be fair to you and fair to your opponent. So a game is fair. This is the definition. You may disagree with it, but this is the position taken in this example. Fair in the sense that on the long run, you will not gain. The average that you will get will be 0. Okay, so this is this is a fairly good definition of fairness. All right, but it doesn't mean it is the only way to do it in here. So I roll a pair of fair dice, and this is 1 over 6, 1 over 6. And so the price I will get will be on the average 3.5. So this is something that we have done because on the average you will get 3.5. Now this is where the comment comes in the previous one. The expected value is not necessarily a possible value of the random variable. So 3.5 is not a possible value of rolling the die, but 3.5 is, at least I don't see anything wrong because it has to be somewhere between 1 and 6, all right? Because the possible numbers are 1 up to 6. So But if I get this number, say 6.5, then I know something wrong with my calculations. So the admission fee, in order to offset the price, should be 3.5. All right. So you have to pay 3.5 per game. Then this game would be fair to yourself and also to your opponent. Okay, I will skip this because I think this is not it's not very helpful. So if you can see the relationship between how you should pay per game and the expected value of the number you get, if you can see it, then you can skip this slide. But if you find it a little bit difficult, in the previous explanation, you can try whether this will be helpful. All right, but I think the one that we just went through is probably very is okay. Okay, the question is, should we play a game of chance with these conditions? It costs us $1.50 to play, and the awarded prize is 1, 2, 3. Now the probability of winning each prize is 0.6, 0.3, and 0.1, so respectively. So the first thing is we wanted to tabulate this. Now, if you don't like using R, but you can use actually Excel to do it. So this will be your X, your column 1, 2, 3, okay. And then the other column you write down the probability. Then what you need to do is just multiply corresponding cells on the same row and then add them up, right? So this can be done if you are more comfortable with Excel, you can do so. So this is, it worked out to be the expected value is equal to 1.5. And so the cost and the expected price is the same, and then the game would be fair. I think this is just add the comment here. We can play the game. I think in all the game, if you are playing with gambling institutions like a casino, I think all games are unfair to you, all right? Because the payoff is actually less than what you do. With possible exceptions of one game called blackjack, because I have mentioned that the blackjack is, did I mention to you about the blackjack? The blackjack has a very strict rule for the dealer, because when the dealer, everyone gets 2 cards, including the dealer, and then the player have a choice whether they would like to draw a card or they stop, or even split if they have a pair of numbers. But then now for the dealer, they have a very strict rule, as far as I know. If the sum of the 2 cards is 16 or below, the rule says that they have to draw a card. All right. So even if it's 16, and even if you know the next card is 10, then he has to draw it, and so he will be busted. But when it is 17 or above, he is not allowed to draw a card. So the rule is really actually, you can ask a robot to play. I mean, there is no decision on the dealer part to make some kind of adjustment. Now, so if there are, and also in casino, in some situations, because they wanted to save time in shuffling the card, they actually don't shuffle it after each play. If you are very observant about the kind of cards that have appeared, so that means the cards that you saw will not be in the deck of cards that the dealer is going to get. Now, some people do some card counting, like big card or small card, okay, just a simple way of doing it. But if you have very good memory, you can devise something more elaborate. So one way is if you count the number of small cards that you have seen. Now, if you have done some counting, and what it means is that if you've seen a lot of small cards on the table, that means a lot of big cards, big numbers will be in the remaining the remaining cards in the deck, right? And so since you are a player, you can actually make a decision whether you want to draw the card or you don't want to draw the card. And if you see that your dealer is very close to 16 but not exceeding not 17 or above, that means he has to draw a card. And if you predict there are a lot of big cards in the remaining cards, then one strategy is not to draw the card, even if your sum is small, because the idea is trying to pass the big card to him, and he is forced to draw a card, and then he busts, and you will win. So you don't need to beat him by the sum, but you beat him by the fact that he busts his blackjack. So that is where I think a lot of movies have been made to this effect. People count cards, and then they gang up together, because then they have an even better control of the cards. All right. Now, supposedly, the players cannot communicate to one another, so this is illegal from the casino point of view. All right. So now this is another example. A private pilot wishes to insure his airline for $1 million. The insurance company estimates a total loss may occur with this probability, 50% with certain probability, and so on and so forth. So the insurance company have to pay the claim from the pilot if there is such an accident. So from the company point of view, he wants to make sure that the premium the insurance company want to charge them is reasonable enough. The first of all is that try to cover whatever the expected damage, expected claim, and then add on it a profit of $5,000. All right. So the first thing we wanted to calculate is what is the expected claim size. So this is this probability for total wreckage of the plane. So the insurance company has to pay this amount of damage, $1 million, and then $500,000 with this probability, and so on and so forth. So this is a simple calculations. Now there is one probability that is not given earlier, is the probability that nothing happened to the airplane at that point of time, maybe during a, say, 1 year period of coverage. So this probability can be found, but this probability is actually not useful in your calculations because the claim would be 0. So no matter what the number is, it's not going to affect your calculations. So this is 4,200, and so the insurance company wants to charge the premium 9,200 here. Now, so this is just a glimpse of how probability is applied, and in fact, in a lot of insurance or actuarial, people do use a lot of probability. Now, this is just dealing with the insurance company towards one company. But from the insurance point of view, he has many clients. He has many insurance policies. Now, of course, they collect the premium. But also they have to set aside a certain amount of money that they have as for liquidity, that they can actually pay the claimant. But they don't want to put everything on the table, right? Then they don't make money. So maybe they put 85% of the money that they have collected into some investment. And now, of course, the investment also have to be whether it's long-term or short-term based on how liquid it is. So one of the things they want to estimate is, will they be able to meet the payment of the claim? So they have to set aside a certain amount so that to offset the possibility of the claim. And the claim size might also is random. The number of claims is random. The size of the claim per claim is also random. So the insurance company wants to make sure, certain that their book is always positive in some way by collecting the premium. So this would be a different kind of calculations, much more elaborate. But then this is basically a very simple way of doing it. So probability and all this comes very naturally in the insurance business. So here, this is a little bit interesting. I've not encountered a couple like this. So So your young couple are planning to have children. The couples are interested in the number of girls that they will have, and each couple agrees to have children until one of the following stopping rule is met. All right, the couple has at least one child of each gender. So suppose they have a girl and then a boy, then they will stop having children. Or they have girl, girl, girl. Well, they according to the second stopping rule is that they stop. All right, or three boys. So this is how it is like. So either the couple will have three boys, then they will stop, or they have a boy and then a girl, then they have two children of opposite gender, so they are happy with that, and then they stop, or girl, boy, and so on and so forth. So we can work out this, but now this is the experiment that I'm thinking of. So these are the possible outcomes according to this experimental rule. Now, but this is not the main interest. The interest is the number of girls and children respectively. So X is more interested in how many girls a couple has. All right? And then Y will be the total number of children. So this might be interesting to the country because they are looking at the reproductive rate here. And so let's just fix our eyes on the random variable X. So X is counting the number of girls. So here you will have no girl. And in these two cases, so this is 1/8 because it is 1/2, 1/2, 1/2. And in these two cases, three cases, you will have one girl. All right? The second possibility here is probability 1/4. And this is 1/4, and this is 1/8. So as a result, I have 5/8 here. Okay, and we calculate it in a similar manner. So you can just concentrate on this table, and so we are able to find out the expected number of girls. So the expected number of girls is 1.25, and then similarly, the number of children will be either 2 here or 3 here. 3 will correspond to this case, and then the last 3 cases, okay, the last 3 outcomes, and so this would be 1/8, 1/8, 1/8, 1/8. So this is 1/2. As a result, because it's either 2 or 3, so if this is probability half, the other possibility must be half as well. But we can verify it because this is 1/4 and this is 1/4. So sum of two 1/4 is half here. So we can calculate this. So 2.5. Okay, so looking at this, we have. Okay, I think this question is a little bit unclear to me. Whether the question is asking the same setting here or is a new question itself. A new question is the couple will always have children until they have the first girl, all right? My elder sister has 3 boys and she really wants to have a girl, but I mean she has given up. All right, so I'm not sure about the question here, so as a result, I don't quite know how to answer it. But let's say if I take this question as part of this example, that means basically X is counting how many girls, and then Y is counting how many boys. So I would be able, Y is counting how many children. So I would be able to calculate how many boys on the average, this type of couples strategy of having the next generations. And that would be the expectation of Y minus X, the number of boys. All right. Okay, here this is just a numerical example. So you have to pull out the example 3, and then now we were told that the density function is equal to 1/2 times e to the power minus x over half. So that is our this is the probability density function. And this probability density function is only defined from 0 to infinity. From minus infinity to 0, the density function is 0. So it would not enter into our calculations. So here we have to do the integration here. To deal with this kind of integration, we use integration by parts. Have you learned integration by parts? All right. So, okay, so let me do the calculation here a little bit. So I can think of it this way. Now, it depends on how you, proceed with your integration by parts. This is usually my way. And I'm thinking of differentiating something that would give me this, all right? So this would be e to the power minus x over 2. So I guess the form first. And now when I really differentiate it, I would get minus half e to the power minus x over 2, right? But I really want just this. So that means I have to multiply this one by minus 2 to offset this quantity. And I still have an x here. Okay, so I have a half. And then according to the integration by part formula, I still have to carry the half. And then I switch these two functions. Okay, and so we can work out this term. And then now this 2 minus sign will cancel with each other, and then the 2. So here basically I have to do one more integration. All right. Okay, so I think this is manageable. Okay. And the probability density function of a Wrigley gravel sales X is given by this. So we are interested to find the expectation. So, so again, this would be just integrating it. Now, the first thing you have to be really watch out. So this is just something very mechanical, all right? Just recalling the definition. But the next thing that you have to really pay attention is over what limit you should apply the formula for the density function, because it changes from interval to interval. So here it is 3/2 times 1 minus x squared. But this is only applicable over the interval 0, 1. So let me repeat it again. In my last lecture, I advised you to really pay attention to the integration limit and what are the formulas for the density function you should put it in. Because if you make mistake at this stage by rushing it, then what you are going to get is likely to be a mistake. And even if you get it right, it's just a mistake, cancel another mistake. So I don't think we will give you a full credit for the final answer because something went wrong in between. But if you make sure you get this run right, at least you're on the right track, and we will give you partial credit for getting it right, even if you screw up in the integration later on. So the probability density function of a continuous random variable is given by this. So that is why you have to be careful, because now the density function has 3 expressions depending on whether x is between 0, 1 or 1 and 2 or elsewhere. All right, so find the average number of hours that the family run their vacuum cleaners. Okay, so we can ignore minus infinity to 0, all right, because the density function is 0. It will not contribute to the to the integration. And then from 2 to infinity, also it won't happen. But we have to break the interval from 0 to 2 into 0 to 1 and 1 to 2, because the density functions takes on different form. So between 0 and 1, the density function is x. So combined with this x here, you have an x squared. And here, so once you are here, then it is just your high school kind of exercise of the integrations. All right. So we have 1. Now the 1 here is actually has a certain unit, so you have to watch out because so it is the average of 100. Okay, in units of 100 hours. So this is the unit here. All right. So as a result, the average number of hours using the vacuum cleaner is 100. All right. So you fill in the unit at the very last stage. All right. Okay, properties of expectations. Okay, if A and B are constants, meaning that it has is not random, and expectation of linear combinations of the x is equal to the same linear combination of the expectations. All right. One example would be the following. I think people you have grown up since young with the SI unit, so we always used Celsius as our temperature. But in other parts of the world, sometimes people use Fahrenheit. There is a way of changing the Fahrenheit to Celsius and vice versa. So it is a linear combinations. So what it says is that if your x is measured in Celsius, but your interest is in Fahrenheit, then you will be having this kind of a change. So what this formula says is that either you apply the formula and change all your numbers to Fahrenheit first, and then find the expectation. So this is your left-hand side. Whereas the right-hand side is you find your average first based on Celsius, and then using the same formula to transform it back to Fahrenheit. So this is actually the meaning here. So so we have a big word for this to summarize this statement. We call expectation is linear. All right. So linearity of the expectation. So you can just memorize this. I mean, it's like a slogan. All right. Here, I wanted to fill in one little step here from the second, from the first equal sign to the second equal sign to bring out the situations a bit clearer. Okay, so expectation of A plus Bx is by definition A plus B small x times the probability of x equal to small x. And so this is the step I want to fill it in. So we multiply this one in first. And then now some of these things, you can do it term by term. All right. And then the next step is, this is a constant. You can pull it out. And this is a constant. You can pull it out. Okay, and you're adding up all the probability, so it would be 1. And here, this is the meaning of the expectation of x. All right? Now, I think in this module, we try to be consistent, but we might miss once in a while. We always try to put a bracket in front after the expectation, meaning that the things that inside the bracket is something that I'm taking the expectation. But sometimes we miss it, okay, because in a lot of textbook, people don't put the bracket in because you have only one thing in in your consideration, so the expectation has to be understood as expectation of x. But whereas here, so if you are looking at expectation of x, there is a possibility of ambiguity, because it might mean taking the expectation first and then square, or squaring it first and then take the expectation. So here we will try to make it clear so that there is only one way of interpreting this one, all right? But very often the context is clear, but if it's not clear, by all means you can check with us. Okay, so these are the special cases. Expectation of b, if b is equal to 0, the translation is 0. Oh, I think we have, okay. I think there is a slight mistake, but the mistake is actually forgivable. Because we were using a for the constant, and then b is the multiplication factor. So we should have set a equal to 0, and then this is b here, then this will be b here. But I think the context is clear. Now this also is useful because you can think of x is a measurement in, say, kilometer, okay, in meter, let's say. And then now, but you want it to be in centimeter. So your multiplication factor would be 100. So here it says that either you find out everything, your measurement in centimeter first, and then find the average of the things that you are looking at in centimeter. Or the original number is already in meter, then you find the average in meter first, and then make the transformation back to centimeter. So that would be the A here. So the A can be can go in and out, all right, because it is non-random. And when A equal to 1, then expectation of x plus b will be just this much. Basically, what you are doing is finding the center of gravity. If you move everything by b unit, the center of gravity will move by b unit as well. So that is the whole thing, all right? So if you think of it in a very physical manner, all this are very intuitive. Okay, so maybe I'll have a break here. So can you come back at 10:55? Then I want to rush through it so that we will finish this chapter. Okay. Okay, very often we are not, okay, let's come back again, right? So we have an experiment, we have the outcomes. And then I've told you that I'm interested in the random variable. And the random variable is sort of a code, coding the outcomes into a numerical numbers. But what we are going to talk about is not this number, it's not this random variable that we are interested, but it is a function of the random variable that you are interested. For example, you pick squares, or squares from whatever you can come across. I mean, like some of this thing. Then, so the experiment you are just picking up squares from a certain populations, and now so the objects are actually in your sample space. The outcomes are different squares. They are geometrical objects. And now I'm not interested in this. The random variable is, since it is a square, I'm interested in the length of the square. So I pick any square in the experiment, and then the random variable is just measuring the length of the square, all right? But now I'm not interested in the square, in the length of the square. I'm interested in the area of the square. Now, in order to calculate the area of the square, you basically square the length, right? You raise it to the power 2. So this is how the situation comes about. At the beginning, you have you have an experiment. That is where the randomness is coming from, the source, the probability. And then now you have a x. X is coding certain things. In my example, x is the length of a random square that you pick from a populations. And I'm not interested in the length. I'm interested in the area. So in that case, I'm actually taking the x to the power 2. And that would be I'm interested. Now, so there's a question is, if I know about the distribution of the length, because it is coming from the square itself, how do I calculate the expected value of the area? All right. So here, this is the way to go. Now, there are two possibilities. Why we wanted to emphasize this is, as it turns out, the two possibilities of understanding it give you the same thing. All right. So this has to be proved, but we are not going to prove it here. So you either do it this way. Okay. So in order to calculate x to the power 8, I'm interested in this number raised to the power 8, and I'm interested in taking the average. So the first thing is, if I take y equal to x to the power 8, y can only take two possible values, either 0 or 1. Okay? When it is y equal to 0, it would correspond to x has to be 0, because y is equal to x to the power 8. And so this would be 0.5, because this is how it was set earlier here. All right? And then y equal to 1 can come from x equal to -1 or x equal to 1. So that is why we are calculating the probability mass function of the y using x itself. Okay? So now we also have 0.5. And so as a result, I will have calculated this by using this table, 0.5, 0.5, and then 0 and 1 here. So I get the 0.5 here. So this is one way, but this way is very clumsy, because what it says is that if I give you a transformation, the first thing is you have to find the table according to the new transformation, the y here. Now this example is easy, but other example can be difficult. You have the original table, but it is according to the x itself. So the best thing is making use of the table. Okay, so so this is the procedures that this slide is trying to emphasize. The procedure of going through a new random variable y equal to g of x and find its probability mass function first before we find the mean. So this is clumsy, because you have to go through finding a new table in terms of the old table. Okay, so this is the definition. not really a definition, but actually this is being deduced from the principles of probability. So for any function g of x with probability mass function in this form, then so again we have to distinguish it whether it's continuous or discrete, because we do things in a little bit differently. The expectation of the function of x, g of x, will be just change your x here in your definition to g of x. So you just follow whatever it is, and this is this, multiply with the probability. So this is a weighted average of the function of your x, all right? The same function. And here it would be the same here, but except that now I change my summation sign to an integral sign. We will spare ourselves from proving this, because this definition will be consistent with these procedures. Earlier, the procedures is we go back to form a new table that corresponds to the y, and then from the new table or from the new curve, I calculate the mean of the new thing. All right, and it says that we can skip this step actually by directly doing this. All right. So this is a bit more direct to do so. Okay. Now we are going to introduce this. This is a very special transformation. G of x is x minus the center of gravity of the random variable x squared. Okay. So you can think of this as the square deviations of the random variable from its own center of gravity. Okay. So this is the square of the deviations. Another one would be g of x is x to the power k. K can be 2, 3, and so on and so forth. So this is called the kth moment of x. There is one other, which since we are here, so another possible way would be g of x equal to x minus mu of x, the mean to the power k. And so later on, this will correspond to the kth central moment. All right. For those who have learned some probability before, when k equal to 2, you are now looking at the second moment in the definition of the slide. But here, in this case, is the second central moment will correspond to the variance of the random variable. So the variance is nothing but the second central moment, all right? We will define it because the variance and the mean of the random variable in many cases captured the random variable very well, especially for normal distribution. For normal distribution, once you have the mean and the variance, you actually define, you know what is the random variable, okay, provided that you know it is a normal distribution. So it is completely characterized by the mean and the variance. Okay, so let's have some exercise here first. And so here you have to calculate the expectation of x squared for this exponential distribution. We will mention this name when we come to either chapter 4, some common distributions of random variables. So this is an exponential distribution, and I'm interested in finding the second moment. Now here you have to really do the integration by part twice, because each time you will reduce the power here. If you do it once, because when you do the integration by part, integral u dv is equal to uv minus v du. So you will differentiate x squared. When you differentiate x squared, it will come out as an x. So the power is actually reduced from x squared to x. And later on, so you have to do it one more time, from x to the power 1 to x to the power 0, and then that would be a constant. So the x will disappear from the integration. And so you will be basically integrating the exponential function alone. Okay, so it's a little bit tedious, but it's good exercise. If you, after your NS, you have forgotten most of your integration. So now it's time to revise them, all right? The expectation of a random variable x tells us something, but not enough, okay? It's a highly summarized thing. So you basically, if your random variable is a discrete, you have a table, right? Table of values, and then tell you what is the probability that one value will likely to occur. And the mean is the expectation is just a summarize of this table into one number. So you'll be able to see why the information of the expectation of a random variable does tell us something, where the center of gravity is, but it will not be enough, all right? So for example, here I have two random variables, and I have two tables here, and both of them give me the mean equal to 0, but the two random variables are very different, all right? So knowing the mean does not mean you know the random variable. You are just summarizing everything into one single number. So it would be too much to expect that you can characterize the random variable itself. So this is just a very simple example to illustrate this. Okay, here the definition comes in very quickly, but let me explain the situations here a little bit more. Okay, so this is your random variable x, a certain value, and here is measuring from its center of gravity. So this is a deviation from the random variable's center of gravity, or its mean. All right? And so here we are going to have a square of it. There is a good reason why we do this. So we are having a square deviation. And then if you are thinking of taking the expectation, the meaning of this is the average. So, so whatever the variance is, so this is what we call the variance of the random variable x. So the variance of the random variable is nothing but the average square deviations from its center of gravity. All right, so this might be easier to think about it. Now, if also you are trying to borrow, but I've forgotten my physics. I mean, it's very similar to your moment, basically. I mean, the moment that, suppose this is your center of gravity, and then you put something on here, this will exert a moment at the center of gravity. So basically, it does have a physical correspondence here. Okay, so let me repeat. X minus mu x is the deviations from its center, all right? And then having a square here would be a square deviations from its center of gravity. The expectation is just you're thinking of it as an average. So it's the average square deviations from its center of gravity. Now, the actual calculations depends on whether it is discrete or continuous. So for discrete case, again, you use summation sign, and then for discrete, continuous case, you use integration. Okay, so that is the only difference. Now, why do we use square deviations? Because let's look at this. Okay, since I'm interested in the deviation, so shouldn't I just compute this? But if you're computing this, this is following from the linearity of the random variable. So this is a constant, so we can move it inside, outside. But this is equal to mu x. And this will be equal to 0. So if you take the average deviation, it will be 0. And it has to be because mu x is chosen to be the right one, to be the center. So if you are taking there are something almost the same thing on one right-hand side and something similar on the left-hand side, and so they will cancel perfectly. Now, so if our idea is to measure some kind of a deviations, because if your random variable, this is your center, and if you have this and this value, if you are comparing this, the same mu x, but if it's somewhat like here, So you want to tell these two things apart, because these things, the mass are very spread out from the center of gravity, and this thing is more close to the center of gravity. So you want to tell them apart. So and we see that we can't just measure this, because it will always give us 0 in both cases. So one way to go about it, of course, is to take the absolute value, because we don't want the cancellation of the sign. But people recognize it. This is very difficult to compute, because you can't remove the absolute sign very easily to do calculations. So a compromise. So this is called absolute deviations. Mean absolute deviation. And sometimes people call it MAD, all right? Okay, it's really MAD. And so a much easier calculation is because the whole idea is trying to remove the cancellations, the internal cancellations. So having a square will do the job too. And now mathematically, having a square is much easier, because I can expand out the square and then do the calculations. So that is why people are interested in this. Now this is going to be the variance, but later on, the variance is measured in the wrong unit, because if x is measured in, say, meter, the expectation here will be meter square. So it's not the same unit as your original measurement. So that is why they have to take a square root of this, and that would be the standard deviation. And the standard deviation will be in the same unit as your original random variable x. So suppose your random variable x is in meter, then this will also be in meter. But whereas here it will be in meter square. Okay, we will come to the standard deviation in a while, but let's deal with the variance. So the variance, the first thing is the variance is always non-negative. Okay, so if you calculate your variance somehow and it is negative, something wrong, all right? The reason why it is non-negative is because this is the probability mass function. It represents probability, so it is non-negative here. And this expression is also non-negative. So as a result, when you're adding non-negative things, it can't give you something negative. Similarly, for integral, your probability density function is non-negative, and this part is also non-negative. So everything in your integrand is non-negative. So when you're integrating things, it will also be non-negative. So we have this property, all right, part A. Part B is another convenient way to compute the variance of x. The variance of x can be seen as the second moment minus the square of the first moment. All right. So you can remember this in word. Okay. So the variance of x is the second moment minus the square of the first moment. All right. Now here is the advantage of having a square. This is the first instance. Okay, so I can multiply out this guy because I have a square. So I will have x squared minus 2 times x mu x plus mu x squared, right? So this is just expanding out the square term. And we have seen that when you take expectation of a sum of terms, we can do it term by term, all right? So we are doing it term by term. So this is the first term, the expectation. This is the expectation of the second term. There is a little jump in the step. I will fill it up. And then the expectation of this. But this is a constant, so the expectation will be just itself. All right? And here I'm taking expectation of minus 2x mu x. Minus can be taken outside. The mu x is a constant, so I can take it outside of the expectation. The factor 2 is also a constant. So in the end, I take out this factor minus 2 mu x outside my expectation. And here now, the next step is to simplify this. Expectation of x is just mu x, okay, our notation. So that would be minus 2 mu x squared. But I have a mu x squared in the third term, so they would cancel out. So in the end, I will have expectation of x squared minus mu x squared. But mu x squared is just another name for expectation of x. All right, so okay, so this is quite an easy proof, and also it illustrates some of the property that we mentioned about expectation. We can always either expectation of a sum of things or the sum of individual expectations. So the two operations will give you the same answer. Okay, if the variance is 0, meaning that if you are taking up the variance as the average of the square deviations, and if the average of the square deviation is 0, basically it says that there is no deviations, right? Because there is no cancellation, first of all. And so the average of the square deviation is 0. That means the square deviation has to be 0. Or in other words, the deviation has to be 0. And so as a result, the random variable is not interesting. The random variable is actually taking one particular number with probability 1. And this is what we call a degenerate random variable. The random variable actually is putting everything in one spot, and this is actually there are no other possible outcomes of the random variable. Now, if I have a linear transformation of this, something that I mentioned about changing Celsius to Fahrenheit, so you have scaling factor, B is the scaling factor. But then because Celsius use 0 as the freezing point of water, and then Fahrenheit using 32 degree Fahrenheit as the freezing point, so their 0 point are not the same. So the A is basically adjusting the 0 point here when you are converting Fahrenheit to Celsius or vice versa. And now here it says that the variance of a linear transformation, you can ignore the translation. A is the amount that you are translating. Because you are measuring the deviation, if you are translating it, the whole thing would also be translate the same amount. And so the deviation will, the amount that you translate will be canceled out. Is that all right? Okay, now you calculate the original center of gravity of this. And then B is just change the scale. And then A is just moving your center of gravity by a certain amount of A. And now you look at all the values of this new random variable. This new random variable is also moved by A amount from your original one. So when you are measuring the departure of the deviation of the new value from the new center, the A is actually cancelled out because you are moving everything the same, right? It's just like you are changing the origin. So, and if you apply to everyone, I mean, the separation is still the same, except that the actual value is not the same, right? Is that okay? I mean, for example, I give everyone 50 marks as your baseline. And your mark difference between two students will still be the same as whether I give everyone 50 marks or not 50 marks. So the A disappear. That's more important, all right? And why do I have a square here? Because you remember that we are talking about the square thing. So the B, even B might be negative, but now you have a B square, all right? So this will always be positive. And it has to be, because we know that the variance is non-negative. So I know the left-hand side has to be non-negative. So you can't have a B here because B can be negative. And so if you forget about the form and if you think that this is B, it can't be right. Because if your B is negative, your right-hand side is negative, but then your left-hand side is positive, right? So it can't be right. Okay, so here we are defining it. I think we have a slip of our notation. So VAR stands for big V here, all right? So, so this is now, you can see, this is the random variable that you are talking about. minus its center of gravity, which is the expectation here. And then you can see if I take the, and the expectation of A plus Bx is equal to A plus B expectation of x. I think we skip a step here, okay? And now the A is actually cancelled out. So this is exactly what I was saying. I mean, you move everything by A unit, and I'm measuring the interdistance. So the interdistance will not matter. So as a result, I have the A cancel out, and then I still have the B, but I can factor out the B, and then I'm under a square here, so I pull the B outside the square, so I have a B square, and so I have this. Okay, so we have an urge to make things into the right unit. Okay, as I mentioned to you, the variance is not in the right unit. It's the square of the unit of your measurement, original measurement. So we wanted to change it back. So we take the standard, we take the square root here. So that would be the standard deviations. Now the standard deviation and the variance only differ by a square root operations. So we can actually apply the same argument. The standard deviation is always non-negative. Okay, part A. And then part C, if the standard deviation is 0, again, the random variable will be degenerate, and it has only one number. Okay, it won't take more than one number. Okay, so this is just the mechanic of doing this. So okay, if you are more like algorithmic, so this might be one way to do it. Especially, you can do it in a table manner. So I'm interested in this guy. Okay, and then I just have the x. I have minus 1, 0, 1, and 2. And I have the probability. This is 1/8. This is 2/8. And this is 1/8 and then 4/8. Okay, so one way you go about it is that this is y. Y is equal to x squared plus 2. So you change this value, and so this is square, and this is 3. This would be 2, and this would be 3. This would be 6, right? Okay. And now, if you are interested in taking the expectation of y, this is what you are going to do. So you multiply it this way, and then so this is this. All right, and so on and so forth. So if you are doing it in an Excel manner, first you create a column or row in this way. And then this is the probability that you have to respect. And this is the transformation. So you have to transform these numbers into the y numbers. And so now you just make use of this and this to compute this. All right. So I think many of you probably are more familiar with Excel than I do. So, so this is how you get it. And now to calculate the variance, to push it further, one way you can do it. Now this formula is in some way it is easy, or in another way, if you're doing it by hand, sometimes it saves you the subtractions at every stage, because you have to do subtraction at every stage. So let me look at what is the expectation of y first. The expectation of y is equal to so the expectation of y is equal to Okay, it's 17 over 4. Okay, so another way is to, if you have, so what you do is now you have a y square. So you proceed to have another table. And now here, in order to find the expectation of y square, now you multiply this number with this number and do it this way, and so on and so forth. So, so if you expect yourself, you are going to compute quite a number of situations in this way, and you might be changing the formula. It might be worthwhile to do it in an Excel manner, all right? So what we are showing here is more like not really algorithmic, but based on the definitions. Okay, so we go through this. So again, here, because we were asked about the variance of part A, so we have to compute expectation of x and the variance of x. So we do this, okay, and so this turned out to be 1. And now the variance is the average of the square deviations from 1, all right? And so I have this. So this is what I meant by using the definition of the variance. You have to do subtraction at each stage. So you have an extra operations each time. So if you're doing it by hand, it is a little bit more troublesome. But on the other hand, there is an advantage of doing this. If your x can take very large values, and if you, of course this is not a problem nowadays. Suppose the numbers are very big, it might be easier to deal with smaller number by x minus the mean, because then you reduce the number to a smaller number and the operation. But this is getting less and less an appeal, because your computer, your calculator can handle a large number of digits. Okay, so this is 5 quarters. And so alternatively, we do it this way. So these are very mundane kind of calculations. And then expectation of y would be like this. So now if you look at this, this is essentially what I was doing in a table form. I was changing this to 3, and then I was changing it to 2, and then I was changing it to 3, and I was changing it to 6. So this is actually what I was doing earlier in a table manner. I guess it is probably more an appeal to you in a table form for computer science students. That is fairly natural. You either think of it as a table, you think of it as a list, so it doesn't really matter. So we can compute the expectation of y, and it turned out to be 17 over 4. And so we do the same likewise, and it turned out to be 51 over 16. So these kind of things are very routine. I don't want to bore you to death. Now this example is basically a continuous example, all right? So you have to watch out that this definition, the density curve, has 3 formulas depending on these 3 intervals. So one is taking this expression, x over 225, when x is between 0 and 15, and then the other is this. So if you actually plot this, this is a triangle. I mean, it is rising from 0 all the way up to 15. When it is 15, it's 1 over 15. And then it's coming down to 0. So this is this. This distribution, sometimes people call it triangle distribution. Right? Pretty obvious, right? So, or think of it as a tent, all right? So, so you have to do the calculations. So I think it's pretty routine to do that. And again, for those fresh from NS, you may want to practice your integration a bit more. I mean, to get into the back to the university time. okay, and so on and so forth, okay. So let X denote the amount of time for which a book on 2-hour reserve at the science library is checked out by randomly selected student. And so the density is X over 2. So the density is actually rising from 0 to 1, all right? Okay, and so we are interested to find out the expectations, the variance, and the standard deviations. If the borrower is charged an amount by this square of the time borrowed, then how much is the expected charge, all right? So for part A, expectation of X will be the only concern is between 0 and 2, all right? So we have to figure out what are the things we are integrating. By right, we have to integrate from minus infinity to infinity, but the density function is 0 outside the interval 0, 2. And then the density function is taking the form x over half, so I have this. And so it's just a straightforward calculation. It is 4/3 here. And then the expectation of x squared. Why do I need this? Because I'm aiming at the variance, which will be the second moment minus the square of this number. So I need to have this number, all right, which is 2. And so, so it's 2 minus this, all right? And so as a result, the standard deviation is square root 2 over 9. And similarly, the expectation of the charge collected would be just this, because of the way it is charged square. So it is already found earlier, all right? This is found here. So then we just record the result here. And if you don't quite remember that you have done it, it's also not a big deal. You can redo it again, all right? Okay, example 20, a jewelry shop. Let me have a peep. Where am I first? Okay, I think I will just finish these sections, and then the shabby shop will be, we have to wait, all right? So jewelry shop purchased 3 necklaces of a certain type at $500 a piece. It will sell them for $1,000 a piece, so the profit is $500. The designer has agreed to repurchase any necklace still unsold after a specified period at $200 a piece, all right? So, and let X be the number of necklaces sold, and suppose X follows the following probability density function. So this is just this much, and then find the expected gain and the variance of the gain. Now here, this kind of problem, you have to, the information is about the number of necklaces being sold. So you have to work out the profit, or the amount that you can collect from the random variable itself, all right? So the gain G of X is given as this, revenue minus the cost. So you collect, if X is the amount of necklaces, the number of necklaces that you sold, and you will collect $1,000, all right? And then 3 minus X is the number of necklaces that is not sold. This is not sold, and as a result, the designer sell it back to the jewelry shop, and he will collect $200, right? And then this is the amount that he has to pay each one, $500, all right? And so this is just this. This is the part that you really have to read the story clearly, and then you have to do that. Now, so for this kind of numerical, for this kind of story problem, the first thing is, after reading the story the first time, you decide on what random variable you are going to define, all right? And after you define the random variable, you reread the story again, but now fill in the detail of the story according to your random variable, all right? So, so once we have this, then everything will be just mathematics, all right? So this is just reinterpret the story into this formula. So once we have this, then it is straightforward to do the calculations. So the expected gain is $700. And also, we are interested to calculate the expected the variance. So the variance is coming from the second moment. So that is why I have to calculate here, and then subtract out the mean, which is 700, the square of the mean, which is 700 squared. So this is what I was saying. In the old days, if you are dealing with this, the number tend to be very big. But if you were doing the subtraction inside first, you are handling smaller numbers. All right. So, but this is again, if you are using calculator, I think it might be easier this way. Or if you are more systematic, you make a table and then do it. Okay. So maybe I'll stop here. The take-home message is that in story problem like this, after you have to read it first. All right. After you read it first, then you decide from the question that you are being asked, come up with a definition of a random variable. And that is the part that it is your input there. Once you have formulated the random variable that you are looking at, you reread the question again, but translate everything in terms of your random variable. Okay? All right. Okay, we stop here.